All right, so we just saw that if you have a fibration, a Serre fibration, then we get the Serre spectral sequence, and maybe the homological version looks like E2PQ is homology of the base with coefficients in the homology of the fiber. And I guess here I'm assuming that pi1 of B acts trivially, so I can ignore local coefficients. And then the spectral sequence converges to the homology of the total space. And I just realized that these are different P's. So the one is P, the continuous map between the spaces, and the other one is the index. I hope that was not confusing and continues to not be confusing. Maybe not the best choice. But okay, so what do I want to address in this video is just where does the spectral sequence come from? We've seen that spectral sequences can come from an exact couple, from some kind of filtered object, and in fact any kind of filtered object tends to lead to the exact couple, and in practice any exact couple we could have gotten from some filtered object. So where does this Serre spectral sequence arise from? Well, one way to get it is to say that B is the CW complex, and so it has a filtration. Okay, so I can start with B in the base and say that there's B0 sits inside B1, sits inside B2, and so on. And here I really want to think of this as being filtered by the CW skeleton. So B1 is the one skeleton. And all I'm going to do is lift that to a filtration of E. So I can take the preimage under this map P of that 0th filtered piece. It's going to sit inside the 1th filtered piece, and so on. And so this is going to lift to a filtration of E. My poor cat is so upset that I'm doing this right now. I don't know if you can hear her, but so much crying. Okay, so anytime we have a filtration of some space, right, we get an exact couple. So this filtration is going to give us long exact sequence in homology. It gives us a bunch of long exact sequences in homology. We sew those all together. I'm not going to spell that out because we've seen it a bunch of times. But what does that give us? Well, we know we always end up with a spectral sequence starting with HP plus Q of the relative homology for the filtered pieces. Oh, now there are too many P's. Okay, I'm sorry. Anytime you see a P inverse, that's the map. Okay, and then this is P inverse B P minus 1. That's a minus 1, not an inverse. Mistakes were made. Okay, and now we don't necessarily know all about the convergence issues. I haven't proved any of that stuff in detail yet, but we have seen before that under good circumstances, we have a spectral sequence that will converge to the homology of the thing that we filtered. Okay, so this doesn't look like the Serre spectral sequence. If I go back up, remember the Serre spectral sequence said something about the E2 page, and it does not look like anything coming from a filtration of E. It just says take the homology of the base with coefficients in the homology of the fiber. So what's going on here? Well, really, the magic of this situation is finding a nice description, finding that nice description of the E2 term from this E1 term. And I'm using interchangeably term and page here, right? Okay, so in fact, this is what proving something about a spectral sequence usually involves. So you filter some object or somehow come up with some exact couple, and the machinery of spectral sequences takes over and there is a spectral sequence, but you need to convince people that it converges to the thing that you want to actually compute, and B, hopefully come up with some nicer description. And that nicer description might start on a different page. So if you can come up with that nice description, then we can just skip to the E2 page. There's no reason we need this messy E1 page, and start our spectral sequence there. So that's most commonly what people are doing when they're proving things about spectral sequences. I guess I should say, other than doing computations, if you're trying to prove some spectral sequence exists, well, of course, you just need to filter something and there's a spectral sequence. But it's really about finding some nice description of some page so that people can actually easily get started with the computation. Okay, that was supposed to be a D. Okay, so let me just sort of say briefly how that goes. This won't be a complete proof, but the idea is that I want to look at my space that's BP minus 1, and then what do I do to get BP? I attach some cells. Now it sort of looks like a weird alien, but okay, I attach some cells, and then all together, this is BP, right? So I attached some P cells along their boundary to BP minus 1. And the key here is to think about what these filtration quotients look like in the total space. So I want to look at the pre-image, lift that BP up to the total space. Now again, too many P's. Okay, I hope this is not too confusing. So I want to look at these filtration quotients in the total space. And really the key here is that a vibration is locally trivial. So this local triviality is going to say that locally, really over the P cells, where now P is that index, this vibration is trivial in the sense that our trivial vibration is just where we have the total space is the product of the base and the fiber. So, okay, locally we should look like this, that E looks roughly like B cross F, at least nearby. And that'll tell us that really this just looks like a wedge over the P cells of B of SP cross F, just because we've done this quotienting. So we just pinched off all of these spheres, and we have sort of something like that for each point in the fiber. Okay, so then what can we do? Well, we found this filtration of E, so we know there's a spectral sequence with this E1 page. How are we going to get to this E2 page? Well, the Kuna theorem tells us that this E1 page, where we were looking at these relative homologies, really just looks like the chains on B tensored with the homology of F. Okay, so now when we take homology to get to the E2 page, what are we going to see? Well, we should have the homology of this, and that's precisely the homology of the base with coefficients in the homology of the fiber. Okay, so really what was key here was not just coming up with a nice filtration, but a nice filtration that then led us to a nice description of this E2 term. And then, of course, we need to show that the spectral sequence converges and all of that stuff. That's something that we'll deal with later when we talk about convergence in more detail. Okay, so I promised some computational examples, and that's where we're headed next. I think first I need to remind you about some things so that we can look at the examples that I want to look at, and I'm not sure that everyone's seen those in their courses. So the next video will be some reminders, and then finally we'll dive into some computations.